Hi class, welcome to Physics 1. We're lucky to have a special guest with us tonight. Dr. Neutron is here again. It's always such a delight to have him in the studio. What would you like to tell us today, Dr. Neutron? Does this thing work? Is the microphone on? Welcome to Physics 1 class. I will now read the PowerPoint presentation for an hour and a half on video. I'll read it to you. Wow, what's that? I think this is what students want, is to listen to a PowerPoint presentation and then watch me derive equations. Wow, that sounds terrible. We're not going to do that. What I am going to do is work through some problems tonight. So I think that's really what everyone cares about, because you see, I recently had an epiphany. Maybe I always knew it. The epiphany is that maybe listening to physicists read PowerPoint slides for an hour is boring. Sometimes you just have to accept the truth about how things are. My son told me one time, he said, "Dad, that's just how life is." Let's take a look at this problem. In researching the forces that act on flying birds, scientists studied the motion of cockatiels' bodies as they fly in horizontal flight. It means they're flying parallel to the ground. As the birds beat their wings, the bodies move up and down, shown in Figure 1. Figure 1 shows the vertical acceleration of the cockatiel's body during one wing beat, consisting of an upstroke followed by a downstroke. Okay, so let's look at the first one. So right here we notice that the highest acceleration is right here, and this looks like about 25 meters per second squared. That is the acceleration caused by a downstroke, because the bird goes up, presumably when the bird flaps its wing down, the bird goes up. So if the bird's mass is 82 grams, what is the maximum net vertical force exerted on the bird? Okay, well, cockatiel, there it is. Imagine it flying. So on our chart here, the cockatiel looks like the biggest acceleration, either positive or negative. So the one with the largest magnitude occurs here at 50 meters per second squared. So that's going to be our maximum vertical acceleration in the y direction when the bird is flapping down. So what do we use? We use Newton's second law, F equals m times a. We know the mass of the bird, mass equals 0.082 kilograms, and we know the maximum acceleration. And if I look at the graph there, to me, it looks like It is 25 meters per second squared. Okay, so we found F equals ma. We can plug in our numbers there and we can get a number. So that's not too bad. Part B. Let's take a look at part B. What does it say? All right, the bird is held in a level flight due to the force exerted on it by the air as the bird beats its wings. What is the maximum value of this force due to the air? Note the bird's weight. The force of gravity acting on it is calculated using WMG. Result that will be justified in chapter 5. So let's read that again. I usually have to read the problems 2 or 3 times, sometimes more, just to make sure I understand what they're talking about. So the bird is held in level flight due to the force exerted on it by the air as the bird beats its wings. What is the maximum value of this force due to the air? Note the bird's weight. The force of gravity acting on it is calculated using WMG. So let's consider what all is going on in our problem here. So if we have our bird, there's our cockatiel, and apparently they have this weird frilly thing on their head, feathers of some kind. There we go. Great cockatiel. There it is. So when the bird flaps its wings downward there, yes, I like to draw the wings of my cockatiel. Okay, it gives us a net acceleration going up of 25 meters per second squared. But this is after gravity has acted on the bird. So, meaning this is the total force. But what are the forces that compose this? Well, the force of the wings going up, and then there's also the force of gravity. So we know that gravity always goes down. The weight of the bird is equal to m times g. That is pointing down. Gravity always points towards the center of the earth. But yet, the bird, the wings, the force on the wings is going up. So we have the force of the wings plus W, that's going to be negative. So we're summing our forces equals our net force, which will be our net force here. So W, we'll say W is equal to minus mg, okay? So we'll have Fw minus mg equals m times a, our net acceleration. Okay, well, this is going to be the acceleration that we're after. So we'll call this m times a wing minus mg, and this is going to equal ma net there. Okay, so we'll get the acceleration. We're going to cancel all of our m's. They just go away. So then we're going to say that the acceleration of the wings is equal to our net acceleration plus g. G is going down, and it's opposite to the force of the wing, which is pushing up. That's why the bird stays in the air. If it didn't, it would just fall out of the sky. So now we can see that a net, that is the acceleration, the maximum acceleration from our plot, which looked a little something like this. Here is plot, and this one up here to, this was 50, and then right about here, we're going to call that 25. Yes, this was about 25 right there. 25 meters per second squared. Yes. So now we have 25 meters per second squared plus 9.8 meters per second squared. We will add those two together, so it'll be 34.8. So we'll have AW, this will be 34.8 meters per second squared. And the question is it asking for the force or, yes, the force. So we have 34.8 meters per second squared. Then F will equal m times a wing. And we know the mass of the cockatiel was 0.082 kilograms times our acceleration, 34.8 meters per second squared. And we will go right over to Mathematica, and we'll plug that in. We'll just stick it in there, right in there to Mathematica. 0.08. No, type 0.082 kilograms times 34.8 meters per second squared. You can put in the units in Mathematica if you want to. That gives us 2.85 kilograms times meters per second squared, or also that is a Newton. Okay, and what does the survey say? Yes, it looks like we've done it. We've solved the net force on the bird, and I probably said too much. I should not solve that for you, but I did nonetheless. Okay, so yes, we get newtons. 1 Newton. I'm gonna take away this answer there. Forget I said that. I'm not gonna show that. Newton is equal to kilogram times meter per second squared. That's the units of force. You're gonna have to go with significant digits on that. Don't forget that in your final answer. Significant digits. They are significant. So if you were wondering what galaxy is this tonight, the answer is the galaxy is M104, or Messier 104. And this is also known as the Sombrero Galaxy because it looks like a sombrero. Interestingly, it's about 50,000 light years across, and it's located, it is located 30 million light years from Earth. So that means, that means that light from that galaxy that we see today left the Sombrero Galaxy 30 million years ago. That light is just reaching us today, and that's really incredible because if you think about it, human beings weren't even alive then. Dinosaurs had, of course, faded out by then. I think dinosaurs went extinct about 60 million years ago. Oh, well, it's late. But dinosaurs were extinct 60 million years ago. And so 30 million years ago, the dinosaurs were gone. But that's a very long time. It's about 50,000 light years across. So from end to end, it is 50,000 light years across. It's smaller than the Milky Way. The Milky Way is 100,000 light years across. So that means the light that we're seeing today took 100,000 light years for it to reach Earth just from the other side of our galaxy. So as we look back, we can see galaxies that are billions of light years away. Scientists have a pretty good idea of how to tell the distances of these galaxies. So that's how we know that the universe is very old, because if it were younger, we wouldn't see the light from these distant objects in the night sky. The Sombrero Galaxy is located at the southern edge of the Virgo cluster. So if you know where the constellation Virgo is, it's on the southern edge of the Virgo cluster. It's not visible with the naked eye, but you can supposedly see it with a a small telescope. So even a small telescope, you could probably pick this up. You can't see it with your naked eye. It's not bright enough. Most galaxies are not bright enough to be able to be seen with the naked eye. Our nearest galaxy, the Andromeda Galaxy, is only 2 million light years away. So, and with that, if you were out somewhere really dark, you might be able to see it, but you probably need a telescope. And it supposedly looks like something the size of the moon or smaller if you were looking out at the sky, but you would probably need a telescope and you would need to be somewhere very dark. I've tried to find it with the telescope in the city of St. Louis, but there is by far too much light pollution. Let's take a look at the last problem of the night. The trapjaw ant found throughout tropical South America catches its prey by very rapidly closing its mandibles around its victim. Figure 1 shows the speed of one of its mandible jaws versus time in microseconds. Microseconds are 10 to the minus 6. Very important. So, part A, what is the magnitude of the maximum acceleration of the ant's mandibles? Okay, so we want to find the maximum acceleration. The maximum acceleration, that would be, so we, on our plot here, let's take a look at our plot. So let's take a look at our plot here. The maximum acceleration, how would we find that? Well, over on this axis, we have velocity, which is meters per second. And then over here, we have time in microseconds. We know that acceleration is the change in velocity over time. So if you were into calculus, if that's your kind of thing. Some people are into calculus. I love calculus. That's actually the class where decided to study physics. It wasn't physics, it was calculus. Calculus is fun. You should take it. But if you haven't, that's okay, because it's the greatest rate of change of velocity. Where is velocity changing the most on this graph? To me, it looks like here I see the biggest drop in the shortest amount of time. So we go in 20 microseconds. From here to here, it looks like it only changes maybe 20. But from here to here, it goes from about 60 all the way down to 20. So it's changed by 40 meters per second in 20 microseconds. I don't see that anywhere else on the plot. Here, it's only, it looks like that's about maybe 25. So definitely not as big as right here. This is the steepest part. It looks like the steepest part. So we're going to say that if I find my acceleration, so I will draw some points. So if I take this point here, right, and this point here, and I find my slope, okay, so that's going to be delta V over delta T, right, so delta T right there, and oh, I'm gonna get out my drawing pad here. I'm drawing the screen, that looks, it's terrible. So terrible. T, there it is, delta V over delta T. That's gonna equal my acceleration. So we can have, we'll say V1 up here minus V2 divided by T1 minus T2. I've said too much. Too much, or maybe not enough. Okay, we did that one. And plug the numbers in there. Let's move on. Last part of the night, part B. Make it a good one. The mass of the trapjaw's ant mandible has been estimated to be 1.5 times 10 to the minus 7 kilograms. Estimate the maximum force exerted by one mandible. How could we do this one? How would we solve this problem? What equation? What would Sir Isaac Newton do? I'll leave you with this thought. Farewell. I'll see you in class tomorrow. Think, what would Sir Isaac Newton do? How did he wake up with this lipstick on his forehead? Maybe he had no recollection of how he got there.
Thank you, like and subscribe down below.